Tonight we're wrapping up our studies on acids and bases, and essentially we're going to be doing a Roman numeral 5. And Roman numeral 5, we're just going to talk about buffers. And buffers, probably just the first thing we're going to define them. And buffer solutions are simply combinations, or combos of weak acids plus conjugate base, or weak bases with the conjugate acid, but weak acid with conjugate base that uses common ion effect we looked at common ion effect back in the equilibrium unit. It uses common ion effect to minimize I'm just going to skip a lot of letters there. To minimize the effect on pH from adding acid or base. Pretty much any biological system, buffers allow life to happen. Our blood has a certain pH, and even certain things within our bodies have certain pHs. And if we eat the wrong thing, if our body does something weird and the acid goes up, we have buffers that help to minimize the effect that either additional acid or base is going to have. All right, because our bodies need certain pHs to function correctly, and that pH differs depending on what body part you're talking about. So anyways, what we're going to do is basically just an example of this, and then there's a couple things of just preparing a buffer solution. But our example is essentially going to be, if we have a buffer, alright, that's consisting of 0.1 molar nitrous acid. So this is a weak acid. It's nitric's kind of twin brother, but not really a twin. So if we have 0.1 molar nitric acid and 0.2 molar sodium nitrite. Alright, so here's our weak acid with its conjugate base. The first thing we're going to do is, and then real quick, the Ka as well for HNO3 equals 4.5 times 10 to the negative fourth. So the first thing we're going to do is just find out what is the pH of this thing before we even start adding stuff. So if we kind of set this up, we basically have HNO2, and it is going to form, I guess if we add water, now if we have HNO2, kind of like that, we're going to make nitrite, and we're going to make hydronium, or H+. So if this concentration is 0.1 molar, 0.1, and our nitrite is 0.2 molar, that's our common ion. Originally we have 0 H+. This is going to change X. This is going to change positively X, and at equilibrium we have 0.1 molar minus X of nitrous acid. We have 0.2 molar plus X of nitrite, and then we have X of hydronium. Okay, so if we look at our Ka, we're just going to set Ka 4.5 times 10 to the negative fourth equals products of our reactants. So we're going to have 0.2 plus X times X all over 0.1 minus X. Alright, and like we've been doing, we are going to assume that X is small. So because X is small, we're going to ignore that, we're going to ignore that. So really, our equation is simply going to equal 0.2 divided by 0.1 is 2, equals 2x. So that x equals half of 4.5 times 10 to the negative fourth, or 2.25 times 10 to the negative fourth, or our pH, if we take the negative log of this, our pH for this solution is 3.65. Okay, which makes sense. It's a weak acid, so it's not going to be much lower than that, but it's certainly in the acid range. Okay, so that is how we can get just the pH of our buffer beforehand. Now what we're going to do is we're going to add, we're going to pretend our buffer, that whole solution, we have 95 milliliters of buffer. So buffer equals 95 milliliters. And we're going to add 5 milliliters of HCl. Alright, so a strong acid, we're going to add 5 milliliters of that. And its concentration, we're going to say it's 0.1 molar HCl. Okay? Alright, so now we're going to kind of rearrange our equation. We're going to be adding acid on this side. So really that acid is going to react with the nitrite to form HNO2. Alright? So if we look at concentrations, we have 0.1 molar times 5 milliliters, which is going to give us 0.5 millimoles. But now our entire solution is 100 milliliters, so we're going to take 0.5 divided by 100, and we really have 0.005 concentration to start with. Alright? Likewise, our nitrite, if we look back up at our example, its concentration was 0.2 molar. Alright? So we're going to take 0.2, multiply it by 95 milliliters, and that's going to be 1.9, and we're going to divide it by 100, so that we get something that's like 0.19. Alright? And then our nitrous acid, if you go back to the top, it was just 0.1 molar. So we're going to take 0.1 times 95, get 9.5 divided by 100, and this is 0.095. Alright? What's going to run out first? Our H is going to run out first, so our X is 0.005. We're going to subtract 0.005 from nitrate, so we're going to add 0.005 to our nitrous acid. And you're going to see these kind of look a lot like the titration problems that were part of our last podcast. So we're going to have 0 acid left. Our nitrite, we're going to have 0.185 molar. And then our nitrous acid, we're going to have 0.1 molar again. Okay? So that's what happens kind of stoichiometrically. But now what's going to happen is we're going to kind of rearrange this and put it back into really what happens if we have nitrous acid that's existing, kind of our equation up here, with nitrite and H plus. Alright? Because if we have these numbers, we're not going to be able to calculate pH. So our new numbers for kind of our next equation, we're just going to get from our previous equation, or from this balanced stoichiometry. So really at equilibrium, we have 0.1 molar, we have 0.185 molar, and we have 0 hydrogen concentration to start with. This is going to change minus x, plus x, plus x. And then at equilibrium we have 0.1 minus x. We're going to have 0.185 plus x, and we're going to have x. So again, it's kind of the two-step problems that we had in our titrations. So now we can solve for Ka again. And again, Ka is 4.5 times 10 to the negative fourth, and that is going to equal 0.185 plus x times x, all divided by 0.1 minus x. And again, likewise, like we do in all these problems, we're going to assume this x is small compared to the value that we're starting with. So this equation simply becomes 1.185 divided by 0.1, it's going to be 1.85 x. So if we divide both sides by 1.85, we end up getting 2.43 times 10 to the negative fourth equals x. And x is our H plus, so if we take the negative log of that, we find that our pH equals 3.61. So notice what happened is, we started with a pH of 3.65, we added some strong acid to it, and because the pH really didn't change, we know this is an effective buffer. Alright? The pH change equaled 0.0, this was a 6.1, so 0.04. Alright? which is not a whole lot of change in pH, so we have an effective buffer. Alright, we apologize for interrupting your regularly scheduled podcast, but we have some breaking news. Here is a new way to solve buffer problems. In the previous problem, I wanted to avoid this equation. And this equation is actually on the AP sheet, but it's known as the Henderson-Hasselbach equation. And the Henderson-Hasselbach equation is a great equation to solve buffers, but most of the time students really don't know what you're doing, you don't know what goes where. So I found that it's kind of just it almost hurts. So the Henderson-Hasselbach equation, if you look on the equation sheet or in the textbook, you're going to see something that looks like this. pH equals pKa minus the log of your conjugate, or really your acid concentration. And you might just say that HA over your conjugate base concentration. Alright? Or just A minus. But this is basically the Henderson-Hasselbach equation. So the breaking news is, instead of doing this, what we're going to do is we're going to solve for this. And we're really just going to take the logs out of it, and we're going to say that H plus concentration equals Ka, I think this is supposed to be a plus, my apologies, plus log of Ka times our acid divided by our base, so really our acid concentration divided by our base concentration. However, because these concentrations are going to be the same for both of our solutions, we can really, instead of doing concentrations, just go moles of acid over moles of base. And we really just want a ratio. Alright, and we're going to multiply that ratio times our Ka, and that's going to give us our H plus concentration. So if we go back to this problem up here, buffer from 0.1 molar HNO2 plus a 0.2 molar NaNO2, so on and so forth. If we add 5 milliliters, I believe, of 0.1 molar HCl, which is what you just saw worked out, to 95 milliliters of our base. So 95 mLs of base, or of buffer. What is our pH going to be? So in this case, what we're going to do is H plus is equal to Ka, which in this case is 4.5 times 10 to the negative fourth. Okay? And then really we want to know moles of acid divided by moles of base. So our moles of acid, we simply have 95 milliliters of 0.1 molar HNO3. Okay? So we're going to do, let's see, 0.095, so we're going to have 0.0095 moles of acid. And then we have 95 milliliters of 0.02 molar NaNO2, that is our conjugate base, so we're going to take 0.095 times 0.2, and we're going to have 0.190 moles of base. Okay? However, if we add 5 milliliters of 0.1 molar HCl, we are increasing our acid constant, or our acid moles, by 0.005 times 0.1, or 0.0005 moles. Okay? And then likewise down here, if we're adding 0.05 moles of acid, that's going to neutralize 0.0005 moles of base. Alright, so really this ratio is going to become 0.0100 moles divided by 0.0185 moles. If we take this ratio times 4.5 times 10 to the negative fourth, we get 2.43 times 10 to the negative fourth. If we go ahead and take the negative log of this, all right, to get our pH, we find that pH equals 3.61, which is the answer we got using the method I just showed you in the podcast. Okay? So the main thing is this equation is available to you all the time. And I am looking at this, and I think I may have gotten it wrong. This last part should be conjugate base over acid. My apologies. And this is what will be on the AP equation sheet. But notice, if we take the negative log of H+, so negative log of H+, we get pH. And if we take the negative log of Ka, we get pKa. Alright? And then here, if we take the negative log of moles of A over moles of B, if this negative becomes a positive, we are just going to flip our ratio. Alright? So essentially that is how this equation, which I want you to kind of memorize or kind of have in the back of your head, this one, I think it just works easier. It's always going to be the same thing, of acid over base. It's not going to go wrong on you. Okay? I think that's it. So anyways, we return you now to your regularly watched podcast. The last couple things, there's no more calculations. We just have to add a couple things to how we make buffers, and then we'll be done. So I think not Roman numeral, but letter B is going to be preparing buffer solutions. Alright, so a couple things to keep in mind. The acid concentration, so concentration of acid should approximately equal the base concentration, or really conjugate base concentration. So we have a conjugate base there. Notice in our example we had 0.1 molar and 0.2 molar. Those are fairly close concentrations. But our conjugate acid and base, or conjugate base and acid, should have similar concentrations. The other thing that we need to keep in mind is the Ka, or not the Ka, let me repeat this, the pKa of our weak acid should approximately equal the pH of our buffer solution. Okay? So if we wanted a buffer that was a buffer 4.5, the nitrous acid buffer would not work very well, because the nitrous acid buffer, to get the pKa of our nitrous acid buffer, we're just going to take the negative log of 4.5 times 10 to the negative fourth, and it's going to be in the 3.5 range. Okay? So if we wanted a pH with a 4.5 range, we could not use nitrous acid. We'd have to look in a table and find a Ka that has a pK similar to the pH that we want our buffer to be at. Okay? Typical buffers in our body are made up of bicarbonate and carbonate. So a buffer like this. Or I think we have sulfate buffers as well. So kind of a sulfate -2 and a hydrogen sulfate would be its conjugate acid. Okay? So I don't know what the Ka values of either of those are, but again, just some things to keep in mind when preparing a buffer solution. Acid concentrations should approximately be our conjugate base concentration, and the pKa should approximately equal our pH. Okay? That is it on buffers. The question number 1 on the test in 2011 was a buffer question, so hopefully it won't be that in 2012, but we will see.